Welcome to the Deep Dive. Today, we're digging into something pretty amazing, the birth of Scanning Tunneling Microscopy, the STM. Our guide is the Nobel lecture from the inventors themselves, Gerd Binnig and Heinrich Rohrer. And our mission, to figure out how they built a tool to see atoms when apparently everyone told them it just shouldn't work.
Right, that's the fascinating part. People literally said it should not have worked in principle. And their first idea wasn't even about building a microscope. Not at all.
Oh, so what were they trying to do then?
They wanted to do spectroscopy, but like really local spectroscopy on surfaces. They were aiming for a tiny area, less than 100 angstroms across, trying to measure stuff on a scale nobody could really access back then.
Okay, 100 angstroms, so tiny. But classical physics would say getting a stable electrical current across a vacuum gap like that is, well, tricky at best.
Exactly, impossible, classically. So they turned to quantum mechanics. The whole thing relies purely on quantum tunneling.
Channeling.
Right. And the real kicker, the secret sauce, is how incredibly sensitive that tunneling current is to distance.
How sensitive are we talking?
Exponentially sensitive. The current, the transmissivity, it drops by a factor of 10 for every single angstrom of separation in vacuum.
Wow, a factor of 10 per angstrom. That's almost hard to grasp. So, like, you move back just the width of an atom, and the signal practically vanishes.
Precisely. It's that extreme sensitivity. And once they actually proved they could get that stable tunnel current across a vacuum, it only took them maybe a couple of weeks to have the big realization.
Which was?
Well, if the current tells you the distance that precisely, what if you scan? Just move the tip sideways laterally. You could map the surface height atom by atom. They'd accidentally invented a completely new kind of microscope.
Okay, brilliant idea. But making it work, I mean, atoms are small. Everything must shake, right? Vibrations.
Oh, absolutely. That was the monster problem. Vibrations, acoustical noise, anything could throw it off. Their first attempt actually was this huge, very complex machine, low temperature, ultra high vacuum, the works.
State of the art.
Supposedly. But it was too complex. Never actually worked. A total dead end, really.
So the breakthrough didn't come from the fancy machine.
Not at all. This is the best part. The first real proof of vacuum tunneling, it happened on, they called it the portentous night of March 16th, 1981. And the setup was almost comical. Primitive.
How primitive?
Okay, get this. An excicator for the vacuum chamber, basically a glass jar, some Scotch tape holding things together. Seriously.
Scotch shape for atomic resolution.
Yep, and for vibration isolation, they use superconducting levitation, which, okay, that's high-tech, but it guzzled liquid helium like crazy, something like 20 liters an hour.
Wow, so a mix of high-tech and hardware store supplies.
Pretty much. But the crucial bits were using piezoelectric materials. Those let you control movement down to the angstrom scale, and this idea of the minute tip.
The minute tip. How does that work? How do you make sure just one atom at the probe's point is doing the tunneling?
That's the magic of the exponential decay again. Because the current drops off so incredibly fast, that single atom on the probe tip that happens to be just fractionally closer, maybe 1 angstrom closer to the surface, it carries almost all the current, like 90% of it.
So the physics itself picks the sharpest point.
Exactly. Nature does the work for you. It naturally selects the single closest atom, the minutip, ensuring that atomic resolution.
Okay, so they get it working.
Yeah.
What were the first big results? The things that made people say, okay, this is real.
Well, first they saw some clear images of monoatomic steps on a material called kerosene-4. Simple, clean steps. But the real clincher, the one that convinced everybody, was solving the silicon 111 surface problem.
The famous 7x7 reconstruction. That had puzzled people for ages, right?
For decades. And STM just showed it, clear as day. That really turned heads in the scientific community. Fast. And it wasn't just topography, not just the shape of the surface.
All right, you mentioned spectroscopy earlier.
Yes, STS, Scanning Tunneling Spectroscopy. By tweaking the voltage, you can map the electronic structure. You can see where the electrons are or aren't. Binnig and Rohrer called it seeing the color of the atoms. You could map out electron states, dangling bonds on silicon, variations in oxides. It was incredible.
So it sees shape and electronic properties. And did it stay locked up in ultra-high vacuum labs?
Nope. That's another key thing. It quickly moved beyond UHV. People got it working in regular air, in liquids like water, even saline solutions, under cryogenic liquids too.
In water. So, biological samples.
Exactly. One of the early exciting applications was imaging DNA chains, just lying on a carbon surface without destroying them. That was huge for biology.
So it's versatile, conceptually simple, relatively affordable.
Yeah, all of that made it spread like wildfire. It led to this much more relaxed and almost casual perception of atoms, as the inventors put it. Suddenly you could see them routinely.
We went from atoms as abstract concepts to things you could image on a benchtop almost.
Almost, yeah, a massive shift.
And looking forward, the lecture mentions Richard Feynman's vision, the Feynman machine.
Absolutely. Seeing atoms is amazing, but the ultimate goal, the long-term dream inspired by Feynman, is to use that incredibly precise tip not just to see, but to do, to manipulate individual atoms.
Build things atom by atom.
That's the vision. To modify materials locally, non-destructively, maybe even assemble new structures from the bottom up, handling atoms directly.
It really makes you think, doesn't it? What other breakthroughs are out there, maybe needing just a bit of quantum insight and, who knows, maybe some Scotch tape waiting to be discovered.